Okay, welcome everybody. This is class 35. We're getting almost towards the end of this, aren't we? We've got today is the last official day of classes at University of Toronto, and tomorrow is called some people call it Wacky Thursday. It's the day in which that University of Toronto redefines to be Monday. So if you have any Monday classes, your professors may or may not be choosing to do a makeup class tomorrow because of the missed Monday for Thanksgiving. And I will be here just chatting about stuff. It'll be a little less formal than this, but we'll do a team up quiz. So that'll be good. Let me do my share screen. And show what's on the agenda for today. Class 35 of 36, I guess. Today I want to finish talking about standing waves. I want to talk about Doppler effect and the equations given in Akina for that. And then I'm going to do some course review, try to go over some of the things that were hardest. And in fact, the 4 team-up questions, which you should now be able to see well, you shouldn't do it yet, but we'll do it tomorrow. But you can see that there is going to be one tomorrow. They're all kind of just multiple choice questions about things that were a little difficult for you guys during the semester. So I'm going to try to go over that, like things like, you know, torque and rotational acceleration, like I guess the angular acceleration versus the or tangential versus radial, that kind of stuff. And then, of course, rotational inertia. And then we'll talk in more detail about what to expect for the final assessment on December 17th. And here what we can see in this animation is showing the sum of a left-going sine wave plus a right-going sine wave. If at every point you do a superposition of these two waves, you get this wave on the bottom. When they're both lined up, you get maximum amplitude of a wiggly line, and when they're out of phase, then the whole thing just goes to 0. So what's interesting is that any point on a standing wave oscillates up and down with simple harmonic motion, except for the nodes, which don't oscillate at all. So there's a node right here, there's a node here, those just stay stationary, but every other point oscillates with simple harmonic motion. The difference is that the amplitude is a little different from place to place. If you're quite close to a node, then the amplitude of the simple harmonic motion is quite low. If you're at an antinode, then like this guy is, then the amplitude of the simple harmonic motion there is quite high. It's the highest it is at any point on the standing wave. Okay. And again, anonymous attendee, the written part of the final assessment will be on CrowdMark. You'll want to submit it or have to submit it on CrowdMark. Let me just look at my chat window, my participants list, see that everybody's okay. Ah, there it is. Good and good and good. Okay. So I want to do a few polls just to get things rolling this morning. Are you guys ready? Hey, Scott, good, welcome. Good to see you. Yeah, maybe if we have some requests that you want to type into the chat of things that you'd like me to go over tomorrow, or just cool things about physics that you want me to talk about, I can definitely take requests for tomorrow. Okay, so let's do the first poll. Oh, so first, let's talk about standing waves. So standing waves are a form of resonance. There are multiple resonant frequencies called harmonics. The boundary conditions and the speed of the wave determine which frequencies are allowed. We talked about that a bit last time. So we call this sometimes a resonant cavity. And at the ends are usually a forced node, like they are in a string. They can also be a forced antinode if you have a capped end of a tube. Yeah, there's the poll here. So a string is clamped at both ends, and it's in the third harmonic. So it's a standing wave in the third harmonic. And I've labeled little lowercase a and lowercase b as being 2 places you could look at on that sort of standing wave, shown it multiple times, 2 different instants of time. So let's think about the instantaneous velocity of points on the string, which remember are oscillating in simple harmonic motion. So when the string is in position A, sort of labeled there. Is it, what is the instantaneous velocity of all these different points? Let's launch a poll. Is it A, it's 0 everywhere, B, positive everywhere, D, negative everywhere, or D, depends on location? I guess A is when it's at the maximum, right? To answer to Andrea's question. Is positive. Okay, let's end this polling and I'll discuss this a little bit. 5 seconds. So this is a bit of a sometimes it's like 50-50. So well, 42% of you answered A, which was what my answer was, but 44% of you answered D, depends on location. Well, so the idea here is that every point is oscillating in simple harmonic motion, and when you're at the position A, every point is at its maximum displacement from the center. And maybe if we look back at that animation, you can see it a little better. Whoops, where is it here? So it's just like at the moment where the black dot is at the very top, that would be A, then for that instant, every part of the string is actually momentarily at rest, because every part is at its maximum displacement away from the equilibrium position. And that means it's turning around. So when it's turning around, it goes through 0 velocity. Let's do another question on this. This is asking now, read it carefully before you answer. The string is clamped at both ends, plucked so it creates a standing wave, again in the third harmonic. When the string is in position B, so the string is completely flat, what's the instantaneous velocity of points along the string? Maybe just click in this in 10 seconds, please. Three, 2, 1. Yes, much better. This is so 66% of you got this one. So what's going on is it's going down so that all these points, like the node is still 0, right? V equals 0 at the node, but here is going down, this one's going down. This is going right at the point B is going the fastest down, okay? But these points are all going up actually. So they're all at the center. All these points are on this straight line, but these ones have an upward velocity. These ones have an upward velocity, the highest being right there. Again, V equals 0 at all the nodes. Again, V equals 0. It's a little hard to picture, but as the thing passes through 0 is when the string, every point in the string is going as fast as it ever will, okay? Because it's if it's at an antinode, then it's passing through its equilibrium. Okay. And then maybe one last question. This is asking about acceleration. Again, let's read it clearly, read it carefully. A string is clamped at both ends, plucked so it creates a standing wave. Again, m equals 3. Define upward motion with positive velocities. When the string is in position B, along the center there, the instantaneous acceleration of points along the string. Is it A, 0 everywhere, B, positive everywhere, D, negative everywhere, or C, negative everywhere, or D depends on location? I brought my Doppler football for a little later too, so I'll try that. It's a little hell here. So 5 seconds to click in on this one, please. This is a tricky one. 3, 2, 1. Again, this one, because it's either A or D. The one I like is A. So again, this is actually more of a, this is more of a simple harmonic motion question, really, because once again, every point except nodes, because the nodes are just sitting there, oscillates or vibrates up and down with simple harmonic motion. And remember that in simple harmonic motion, when you pass through equilibrium is when you have zero acceleration. It's when you're at your fastest velocity. So the velocity is at maximum. So then the acceleration is momentarily zero at that point. Okay. So A equals 0 at equilibrium. And yeah, it overshoots because of its inertia. That's exactly correct, Faison. Oh, and Naomi points out that the length of the string is actually a variable here. So it's going to be, I guess, shortest when it's at B, and then the string will kind of stretch, won't it? Especially when it's drawn not quite to scale like this. Okay, I'm going to continue on here. This is talking about standing sound waves. A long, narrow column of air, such as the air in a tube or a pipe, can support a longitudinal standing sound wave. And the way it sort of looks is this. You've got the air sort of swooshing back and forth here. And there are places where, and this is, I guess, the displacement of all these air particles, where the particles are getting crowded and then getting less crowded. That's an antinode of pressure. An open air column of air must be a pressure node because it's always at the ambient pressure. And so the boundary condition is of nodes at the end is the same as for a standing wave, but a closed end forces a pressure antinode. That's where this closed end here, closed end, forces an antinode because there's a pressure actually coming from the cap there, and then an open end forces pressure node, which is called the ambient room pressure. Oh my God, what about on? I think I'm on Siri. Oh no! It's the first time that's happened to me. How the hell do I exit Siri? There we go. I'm trying to write on the bottom of the screen here. I'm trying to say that's 1 atmosphere right here at the end when it's opened out to the end, like the end of the flute. Okay. So with a wind instrument, blowing into the mouthpiece will start primary oscillations, which then will drive a resonance standing wave resonance in the tube of the instrument, which then makes a nice sound. And then you can change the notes by actually closing or opening holes along the tube to change the effective length of the tube. And so that changes the effective or the fundamental frequency. So the fundamental frequency, again, this is the same equation as it was before for the waves, standing waves on a string, V over 2L. But here, V is equal to 340 meters per second. It's called the speed of sound. Speed of sound in air. Okay, and L is the length of the tube. Now you can also have an open closed tube, such as a clarinet. So the mouthpiece on a clarinet has a reed in it, which will actually, it has a very, very small opening, and it acts as if it's a closed end. It forms sort of a cap there, whereas the other end has a bell on it and is opened up to the air. So this forms an open closed tube. And what's interesting about a clarinet is that the lowest note for, even though a clarinet is about the same length as a flute, the lowest note you can play on a clarinet is about an octave lower. And that's because for an open closed tube, it's V over 4L. You're fitting a quarter of a wavelength in there. So in both of these equations, V is the speed of sound. You can also overblow wind instruments. You can sometimes get higher harmonics. And the way this works out, just try to show it here. Diagrams of this. So if you have it open, then let me just draw it, I guess. What I'm trying to draw here is that the frequencies, if you have open, we drew it last time a little bit. What they will do is you'll have 1, that'll be your M equals 1. That'll be nodes at the end. Then 2 will be something like that. Okay, you have 1 intermediate node. This is M equals 2, and so this right here is the wavelength. Oops. L equals the wavelength over 2. Whereas this one, L is equal to the wavelength, it's just the wavelength. And then you can also have M equals 3, where you've got, it's a little hard to draw it, something like that. So this length is equal to 3 halves of the wavelength 3. So that's open or closed. For the open closed tube, then what you have, if it's open at one end and closed at the other end, then you'll force an anti-node at the closed end. So what it looks like is this. It just goes up and down. And what this is the length here is equal to lambda 1 divided by 4. It's a quarter of a wavelength for M equals 1. But then, if you overblow the clarinet, you go to the next, if you have an open on one side, closed on the other, you'll have a node on one end, anti-node on the other. The only way to do that is to form something like that. You can see it? So here, the length is equal to lambda, we're going to call it lambda 3, which is, and it's going to be, the length will be 3/4. And so this is called the M equals 3 mode. So what happens is that even harmonics are not allowed in the open closed tube. That's one way of saying it. You can I guess you could just say that M equals 3 is the next harmonic or the second harmonic, but in physics we just call it the third harmonic, and we don't really talk about, we just say evens are not allowed there. That's how that works. Yeah, so in terms of a flute, I think the distance is between the open hole on the mouthpiece and the next kind of open hole that's down there. So it's true that on the mouthpiece there is a closed end, but when you actually blow over the top, that is an open hole, isn't it? So that's where it's coming from. Whereas with so there's no closing wooden reed on a flute. That's what makes the difference. It's more of a open embouchure. Okay, I think that's it. That's all I really wanted to say about standing waves. Pretty much got it. Next is this Doppler effect thing. And in fact, what I wanted to do is start off with something very simple, which is this simulator. So Doppler effect is actually a pretty easy concept. Well, it's a geometric effect, and I've put this simulation on the web link there. So the first step here, let's just look at this. Number one is no Doppler effect. So what's going on is the red dot is the observer and the black dot is the source. And if you start waves, then what happens is that these wave fronts go out into the room and then they pass the red dot at a certain frequency. 1, 2, 3. Oop, that's the end of animation. Let's start again. First it has to get there. But they pass at a certain frequency, 1, 2, 3, 4, 5. So that frequency that they pass is some number, and that's called the frequency of the source. But then a couple of things can happen, is you can take the source and move it along. So this is going to be 3. The source moves toward the observer. So in thing 1, the observed frequency by the person listening at the red dot was the same as the source frequency, FO equals FS. If the source moves towards the observer with some speed, VS, then this increases the frequency. And there is an equation in your book, but can you sort of picture it? So these are now passing faster. Whoop. And the reason is that all of these circles are centered not on the black dot, but they're centered on where the black dot was when it emitted that circle. So the circles are all traveling outwards at the speed of sound, but the position of the source keeps moving so that the center of each circle is further and further to the right. So, oops. Back to 3 again. So as the thing is moving, step forward a little bit, any particular circle is just centered on where the black dot was when it emitted that circle, right? They're just going out. But if you're over here in front of the source, they're all bunched up, still traveling at the speed of sound, so the wavelength is smaller, basically, and what that means is the frequency is higher, because the speed of sound is what it is. If you were behind the source, then you get a lower frequency, and there's an equation for that as well. Until they crash. What's the next thing? Yeah, 2. Observer moves towards the source with a speed VO. This increases the frequency to a slightly different equation. Again, this is in your book, so let's look at number 2. And try that. So what's going on here, which is it's sort of like a different situation really, is that for this observer who's now going through the air, it's like you're going into the wind or something. And so what happens is that as time goes on, you're hitting these things faster. And if you're going away from it, sort of going away from the sound, and the sound's coming from behind you, then it would also be a lower frequency. So the frequency is increased here, but it's sort of for a slightly different reason, if you can sort of picture it. Oops, yeah, that's 2. Let's do 2 one more time. It's still faster. And I think there was one more. Oh, the sonic boom. Want to try that? That's when you're moving faster than Mach 1. And then you see all these, the boom. Okay, so all those wave fronts where the pressure is maximum are all kind of lined up with each other, and you hear this big boom. It's there if there's a jet that's going faster than the speed of sound going over a quarter top overhead. The next thing that I wanted to do is to try a little bit of actually showing this. Stop my share for a second. I have a couple of things. One of them is this, this beeper. So I've got a buzzer that's on a string. So what I'll do is I'm gonna put it in uniform circular motion and swing it around over the top of my head. And so what you're listening for here is the pitch. So the pitch when it's at rest is this. You can hear that. But if it's moving towards you, the pitch might be a slightly higher frequency. And if it's moving away from you, a slightly lower frequency. So let's just, let's do that with me swinging it over my head. Can you hear it? The other way, maybe? I can't hear it because I'm in the middle. So it's always the same velocity to me. The other thing that I have is the Doppler football. So the Doppler football, again, has a little buzzer in it. So that's when it's at rest. But if it's moving, you might hear a slight difference in frequency. So what I'm going to do is throw it towards my laptop. Never a good idea. Ready? Okay. I think much damage. Turn off the Doppler football. So that's what we play football with here in the physics department. All right, let's go back to my share screen. Again, people's dogs are going a little nuts. I don't usually have dogs in my classroom, but that's good. Okay, here are the equations, and we'll do a couple of polls on these. It's one of the little silver linings of COVID is you get to bring your dog to class. Wee-oo, wee-oo. Okay. And this is, sometimes you will hear this with traffic or with a siren going by, is that, or if someone honks their horn, for example, as they're driving by you, it'll go, beep, as it goes away, right? So as it's coming towards you, it's slightly higher frequency. And then if it passes you, I guess it goes through its source frequency. And then as it's going away from you, it goes down to a little bit of a lower frequency. Also, if someone is playing music and really loudly in their car, if they're going past you, it's going to sound just all screwed up because you'll hear this, everything will sound a little higher as it's coming towards you and a little lower as it's going, and it'll just sound all out of tune, and it won't sound good. Now, these are the equations that are given in Atkina in your reading. So let me just go over them, and I've kind of split them out to what this is. When the observer is stationary and the source is moving away at speed vs, then what will happen, so this is actually toward, what will happen is that, so this is source moves toward observer. I like to split these up. What Atkina does is put a plus or minus in these equations, and I find that incredibly confusing because it's just one or the other, right? Or the source is moving away. And the way that I remember these is away from observer is, again, sort of this blue shift versus red shift. You got, if the truck is moving towards you, so the frequency is higher as the thing is coming towards you. Again, those wave fronts are all bunched up. So the V minus Vs, V is the speed of sound. Again, sorry, so V is speed, sorry, speed of sound in air, 340. meters per second, okay? And then Vs is less than V is source speed, okay? So this, it has to be less than the speed of sound, because otherwise for Mach it doesn't really work. If the source is moving towards you, then you'll get a little bit less. Your observed frequency, then the frequency, the denominator is a little bit less than 1, or a little bit less than V here. So you do V minus something a little less than V, you get a higher observed frequency. If you do the source is moving away, then V, this is a little higher than V on the denominator. You've got V up on the numerator, and so this is a little bit greater. Sorry, less. The observed frequency is a little less than Fs. So again, you have to kind of look at this fraction and see what's going on here. Okay. The fraction is going to be a little bit greater than 1 for moving towards, and a little less than 1. The other thing that you can have is, oh dear, I've already messed up this PowerPoint slide, sorry. Do it this way. Oops. When the source is stationary and the observer is moving at a speed VO directly towards away from the source. So this was when the source is moving, like a ambulance siren. So the source is what's moving, you're standing still. You can also have a Doppler effect if you're the one in the car and you hear something stationary that's emitting a sound. It's a little less common, and you get slightly different equations here. So, and once again, you've got V, this is now in the numerator. So V plus VO divided by V, this is when the observer moves toward the source. And this is when the observer, this is a V minus V0, moves away from the source. I'm not going to derive these equations, but they're pretty easy to derive geometrically. And they are slightly different, just because what's going on here, so this, again, VO, which is less than V, equals the observer speed. In this case, the top case, when the source is moving, the reason for the Doppler shift is that the wavelength has changed, but the speed of sound has remained the same. In this case, where it's actually the observer moving through the air, the wavelength is the same, but the effective speed of sound is different because the speed of sound is relative to the air, right? So if you're moving upwind, then the speed of sound of waves coming towards you is effectively faster. And if you're moving away from from a source, then the wind kind of slows down that speed. So you get slightly different equations. Let's do a quick poll. Valerie is standing in the middle of the road and a police car approaches her. So you should never stand in the middle of the road. Usually you're standing off to the side, but Doppler effect is a little difficult to picture, I think, if you're standing on the side of the road, because then there's an angle and everything. With both of these equations, the source is either moving directly towards you or directly away from you. So you have to stand in the middle of the road. Police car approaches her at some constant speed, Vs, speed of the source. The siren emits a source frequency of Vs. What about VO? So is it, put the poll here. A, the frequency she observes rises steadily as the police car gets closer and closer. B, the frequency she observes steadily decreases as the police car gets closer and closer. Or C, the frequency she observes does not change as the police car gets closer and closer. Samantha, I'll get to your question in a second, but let's do another 5 seconds on this one. Okay, going once, going twice. Okay, so yeah, this is a common misconception. So no. So remember, there's no distance in this equation, right? All that's happening here is that there's been a change in the frequency and it's steady. Okay, unless I guess maybe if the police car was accelerating as it's coming towards you, then the frequency would rise. But also if the police car saw you and was slowing down, then the frequency would be steadily decreasing, right? So it's a constant. So and that it is, so F observed is equal to Fs times V divided by V minus V S is a constant with time. So if you're in the 19% who voted for C, you got the right idea. Maybe a bit of a trick question there. Sorry about that. Next one's a little tricky too. This one's a little more complicated, actually. Let's read it very carefully, because this one I'm going to have to go through. Valerie is still standing still. Okay, as a police car approaches her at a constant speed, V sub S. Daniel is in his car moving at the same constant speed as the police car was, but he's going towards an identical police car with an identical siren on it, which is standing still. Does that make sense? So, and they both hear a siren. So they're both going to hear a Doppler shift. I think it's both going to have an increased frequency because they're moving towards, but one is because for Valerie, she's the observer standing still and the source is moving towards her. But for Daniel, he's the observer moving and the source is stationary, but it's the same speed in both cases. So A, the frequency Daniel observes is lower than the frequency Valerie hears. B, the frequency Daniel observes is higher than the frequency Valerie hears. Or C, the frequencies that Daniel and Valerie observe are exactly the same. Maybe I'll write out the equations here. Let's call it PD. Okay, let's end the polling on this. See what people got, and I'll go through it. I say this was kind of a hard one. So let me tell you. Actually, I think C was a good guess. That's probably what I would guess if they're going at the same speed. So let me just say that this pretty close to true. Okay, they're both going to have an increased frequency. Both frequencies are a bit higher. But that's not really what I'm asking. What I'm asking is if you're like 10% higher, like if let's say VPD is 10% the speed of sound, then you're going to have 1 over 1 minus 0.1. So it's 1 over 0.9, for example. Whereas if VPD is, again, 10%, you'll have 1.1 over 1. So is 1 over 0.9, I think you can do it on your calculator, is actually, I think it's greater than 1.1, right? It's 1.11 or something like that. So the answer is that it's A, actually, which was the lowest. I don't know who got A. I don't know if I can show it another way here. I don't know. How can you actually compare? One way to compare, we can do this. We can say, let's compare by multiplying both sides by, I like to get rid of the denominator sometimes, so I can multiply by V minus VPD. So VF times V minus VPD is just equal to FS times V, because it just cancels out. That's the Valerie. If you look at Daniel, then you've got times the same thing. Then what you'll have is FS times V plus VPD times V minus VPD. You got A plus B times A minus B, which you might remember is just going to be FS times V squared minus VPD squared over V. So FD times V minus VPD is equal to FS times V times 1 minus VPD over V squared, which is a little bit less than FSV. So again, Daniel here's a slightly lower frequency than Valerie. Okay. Sorry, but that was kind of a challenging one. Just getting you used to using those equations that are in Epkina. And then there was a good question before from Samantha. How about if the source and observer move towards each other? So what you do then is you say that, I guess what's really happening here is that you use this equation, you use the second equation for the fact that the observer is moving, but then instead of Fs here, you plug in this equation from the top, because now the observer is also moving. You just call this F1 or something and plug it into here. So you've just combined these two equations. You end up with V plus VO divided by V minus VS. And that Adhina actually does that if you look carefully. It's just that she's got those plus minuses on the numerator and the denominator. It's a great question from Samantha Chen. Ooh, we're getting towards the end of this. We're at the end of the course, so that's good. I had a couple of review slides I wanted to go through. So what should we do here? I think what I might do is leave these review slides until a little later. We'll come back to them maybe on Thursday, but there's instantaneous velocity. That was kind of tricky. This angular acceleration business, I'm going to go through this maybe a little bit tomorrow, but you've got two things going on here. You've got the tangential acceleration in meters per second squared, which is whatever your alpha is times r. But whenever anything is moving on a circular path, you've also always got a radial component to the acceleration, which is v squared over r towards the center. And so what happens in this situation, this is going to be on your team up quiz, is that if alpha is non-zero, then you've got your constant tangential acceleration, but you've also got an increasing component towards the center. So you've got a sub r, which is always v sub r. As v, it starts at 0, I guess, when v is 0, but as v increases, your radial component of the acceleration gets more and more. So this ball has a diagonal acceleration. One component of it is tangential, one component of it is radial, and it's actually going off on a diagonal. I'll talk about that more tomorrow. Static friction, that was actually pretty easy for you guys. Gravitational potential energy, again, you guys got that pretty well, but I'll go over that a little bit, how things move. This stuff about collisions. Oh my God. I could watch this meme forever. Basically, if you've got a more massive object colliding with a smaller mass object, then there's the same equal and opposite impulse on both masses, but the change in velocity of lower mass will be much greater. Okay? So that's what happens there. And so I think these the impulse stuff and the collisions was a little difficult, so I'll go over that a little more. This stuff was really tricky. Rotational inertia. So again, on the team up quiz, what I'm going to do is something like that door question that was on midterm 5, is just trying to find rotational inertia of a compound object. So we'll go over that. You just sum it all up, right? Okay, final assessment. There will be a final assessment in this course on Thursday, December the 17th. So you're going to be able to find it on Quarkus. I'm going to make a new module today called Final Assessment. The format will be this. It's going to be a 30-minute multiple choice test, followed by a 10-minute break, and then a 35-minute 2-question written answer assignment to be submitted on CrowdMark. The timing will be as follows. Again, all on Eastern Standard Time, Toronto, 7:10 to 7:45. Now that's a 35-minute window, but you only get 30 minutes within that window to actually do the test. Once you start, you get only 30 minutes. So really it's 7:10 to 7:40 if you start on time. If there's 10 multiple choice questions, then that break. At 7:55, you'll see this CrowdMark will suddenly pop up, and you get until 8:30 to submit the CrowdMark, to write it out, take images, and submit them up. You can do it. So as far as the multiple choice questions, each question will begin with a time estimate, and all of the time estimates will sum up to 25 minutes. Very similar to how that happened on midterm 5. The entire course is testable, so it's going to be random, but I'm going to pick 10 questions, and it'll cover everything from chapter 1 through 11 and all the practicals that you did. And yeah, it'll be pretty easy to, I guess, release the marks for this, but I won't be doing it right away. It's a good question, Sumit. I don't know. And expect a slight emphasis on these chapters 4, 7, 8, and 10 as 4, 7, 8, and 11, as you haven't had multiple choice midterms on any of these chapters yet. Written answer questions, 7:55. Again, you must go through the 4-step problem-solving strategy as given by Atkina and followed throughout this course, writing your answers out on the answer template sheet or a reasonable facsimile. So one of the things I might have time to do on Thursday is kind of go through. I am making a promise right now that the 2 questions will be chosen from one of these following 5 chapters. So 3 of these won't be it, but 2 of them will be it. Either chapter 5, 6, 9, 10, or 11. And what I will do is I will post a document today on Quarkus with the 5 different rubrics that you can have for any of these 5 chapters. Make sense? Because they're all a little bit different. Each question of the 2 questions you get will begin by stating which chapter it's from, so you know which rubric to take it from. And I'll post what the rubrics are today. Make sense? you don't really have past tests because this is the first COVID test ever, right? This is just saying it's good to work with peers if you can, try to find study groups. Best way to learn is to teach. If you can't really explain to someone else what you've done, then maybe you haven't really understood it. It's harder than you think to actually explain to somebody. And tomorrow, from 11 a.m. to 12 noon tomorrow, this is called Wacky Thursday, we'll have a makeup class right here for that Monday that we missed in October. This is going to be sort of an informal course review, going over some of those slides I just showed, maybe some questions that people have asked me, things that have been coming up in office hours. We can do a face filter if you'd like to. Please plan to meet up with your practical pod tomorrow. I'm going to give maybe a little more time, like about 12, maybe 13 minutes in the Microsoft team to kind of have a farewell with your practical group, but also do this team up quiz bonus course review. It might take more like 15 minutes actually, because there's 4 questions. They're worth up to 20 points depending on how many times it takes you to get them. And those are all above the maximum 305. So there's going to be, I guess, 325 total homework credits possible out of 305, but you'll be cut off if you go above 305. If you cannot do the team up quiz during tomorrow's class, it can be done anytime between now and tomorrow at 11:59 p.m. I'm not allowed to assign homework, I guess, during the final exam period, so it is due tomorrow. And I think that is it. Like, what I'm going to do is go to the hands. Great to see all of you. Take care. And if I don't see you, have a great break. And I'm going to turn off my YouTube video here, if I can find my mouse.